I will write the result for this new system down automatically by reading off the results we have obtained for the XZ system. Because as far as the final gadget is concerned, there is no difference between Y and Z. All you have to do is just change the Z's to Y. Here. Sorry, I take it back. The first one is to be replaced by Y, the final Z. Sorry, this is not the correct thing to do. If I'm going to copy the results automatically, I have to change this to Y. Whatever I said before in relation with the X, I repeat, same for the Y. Then what do I get? Following all those steps, now I expand the plus Y in terms of the plus and minus Z's, and then I go and expand block the upper one and take the minus Y and expand in terms of the Z's. I get a very similar expression, but the phases will be different, of course. So, plus Y 1 over square root of 2 plus Z again here, e to the I delta 2 minus Z, and minus Y 1 over square root of 2 plus Z minus I delta 2. Argument was that this is an arbitrary input. It could have been anything, this being an arbitrary as far as this is concerned. There are the bases associated with this one as plus and minus Z. We expand this in terms of those and impose the condition that they must be normalized. And they come out with equal intensities, 50%. The magnitude of the projections are 1 over square root of 2, 1 over square root of 2, gives us this. The second component is obtained by writing this as again as an arbitrary superposition of the plus and Z states with normalization condition coefficient mods square of the coefficients adding up to 1 and being orthogonal to this one. When you apply these conditions together, you get that expression. So we have the plus minus Y states here and the plus minus X states in here listed. Notice that in both of them, we have complex phases appearing. Delta 1 in one case, delta 2 in the other case. Is there any way of determining those phases? Or do we have to have those phases arbitrarily sticking around? To determine the phases now. We have to check whether there is any other information that we have not used yet. What is the information that we have used yet till now? we have used the information x, z, and y and z. But there is how about thinking of the xy combination? If there are three components of the spin operator, if sequential measurement of x and z involves two components, x and z, sequential measurements of y and z involving two sy and z, how about the sx and sy sequentially measurements? So there is yet another information that we can use. That one can use. X and Y sequential. Stengerlat arguments. Sequential SG experiments. So what does it mean if that is the information that we are going to use? What will happen then if we use that information? Let me write that down. We come through an SGX and let it go through an SGY, whichever. You can take this Y to be X anyway. So if you filter out the down component and let the up component pass through, well, out of this, there will be two beams coming out with equal intensities polarized in up and down direction. That's the third system. Notice that we have used the previous two. Now this is the new one. Or you could block this and let it go through. So how do I read that? I read it in the following manner. The probability of getting this is 50%, and the probability of getting this is 50%. Therefore, plus y from plus x, the magnitude should be 1/2. Similarly, minus y from plus x should be 1/√2. This is in relationship with that picture. What about the other one? If I now block this and let the minus one go through, still I will get the equal intensity plus y and plus y, minus y. Then it will be the following. I have further plus y minus x is 1/√2 minus y from minus x should be 1/√2. Because the square, magnitude square are 50% in each. Therefore, if I take the square root, I will have the magnitudes. So what then I can write is lift those mod signs and put the phases, and overall phases are not important. Write the relative phases. Then what do I get? I have the plus x and minus x is given already, and the plus y and minus y is given already determined. I have to take these sets and substitute in here, and let's see, what do I get, for instance? Well, consider one of them. You can consider any other three. Consider the first one here. So plus y is what? This one. There is an overall 1/√2 from one. There is another overall √2 from the other. Put them out. And you have plus z plus e to the minus I delta 2 minus z. I have written this one. plus y in here. This is the cat. When I go to the bra, I change the sign accordingly. It's change the sign of the face. And here I have to write the plus x plus z plus I delta 1 minus z. Okay, I'm just writing the first one here. And there, it should be what? It should be 1 over the square root of 2. Right-hand side. So what is this? Let me multiply them. Plus plus is 1. And there is this 1 over 2 goes there as the square root of 2. So there is the plus plus is 1. Minus minus is 1. But there are the phases. It is e to the I delta 1 minus delta 2. The first one with the last one is 0. The second one. Second one with the first one is 0 because they are orthogonal. Only the first with the first, second with the second gives you something. There is a relative phase in the front in here. You see? Please try to digest the logic behind it. The arithmetic is easy. Let me repeat myself. I have three components of the S. Sx, Sy, and Sc. In the three experiments, I have first considered the xy sequential experiment. In the second one, I have considered the xz sequential experiment. That enabled me to determine the Sx and Sy up to phases. Then I put these two together. X and Y is put together. There. Here. YZ, XZ, and then XY. That's the last one. You see, that will help me determine the phases. Actually, the difference of the phases. There is yet an ambiguity. The quantum mechanics is really strange. There is room for further freedoms, which we call ambiguity. It's not going to determine everything, obviously, because if there are two phases entering, one in here and one in there, this can only, you may say, you are using only one of the equations. Perhaps if you use the other three, it may give individual. I invite you to challenge me and determine whether you may have anything more than this, determining the phase only, phase difference only, not the delta 1 and delta 2 separately. None of the other three equations will give you more than this, involving any one of them individually. It gives the difference. That's the reason why I'm not pursuing it any further. Let me finish this computation. It's not too difficult to see that it's a complex number. It has what? A real part and complex part. If I take the square of it, it's the real part squared, which is 1 plus cosine delta 1 minus delta 2 squared. That's the real part of that inside, which is a complex number. Second part is this I times the sine. You take the square of it, so sine squared delta 1 minus delta 2. Right hand side is the square of the 2, square of the square root of 2, which is 2. Notice that from here I have 1 plus cosine squared delta 1 minus delta 2 plus twice cosine delta 1 minus delta 2 from here. And here's the sine squared, the second term. I'm not doing anything. Let's combine these two terms, which gives you another 1. So 1 plus 1 is 2. So I have 2 plus 1 plus cosine delta 1 minus delta 2, right, is equal to 2. 2's cancel, and you have cosine delta 1 delta 2 is equal to 0. How nice. If the cosine of delta 1 minus delta 2 is equal to 0, delta 1 minus delta 2 is either plus or minus pi over 2, right? Within the full 2 pi period. You may say, if you want, you say pi over 2 and 3 pi over 2, depending on or you go this way. Not only that it's a difference, there's also further ambiguity. There are two possible values that you find, either pi over 2 or minus pi over 2. Well, you may get into rather complicated options, but the trivial solution is you choose one of them to be real. That is, either you choose delta 1 is equal to 0, that's first option, and you get delta 2 is equal to plus and minus pi over 2, or vice versa. You can choose delta 2 is equal to 0, and you get plus delta 1. Well, this is not important, but being very straightforward, you may wish to write it as such. Now we have to resort to the convention. The conventional wisdom, at least at those days when they were constructing these things, they have chosen the first one to be real. That is, the eigenvectors of the x and y are chosen to be real. So the eigenvectors of the y, sorry, I'm repeating myself correctly. Eigenvectors of the x plus and minus x are chosen to be real. That's first option. So that second, that eigenvectors of the sy come out to be complex, that is with imaginary parts also included. This would be the other opposite, but this is historically the one which is chosen. Therefore, choose this. Eigenvectors of x are real and eigenvectors of y are imaginary, implying, using the general representation of operator in terms of its eigenvalues and projectors, it means that the operator itself, Sx itself, would be real. Okay. Implying, let me write it, implying eigenvectors of Sx being real and eigenvectors of Sy complex. Either way, whichever option you choose, obviously, you remember originally we said we need to have complex vector space. Here is a demonstration. We have constructed this explicitly and show that the vector space, or even this simple, for the simple spin 1/2 problem, the Hilbert vector space is complex vector space because eigenvector having imaginary parts in it. This further implies that Sx operator is real and Sy is complex, which we'll demonstrate soon. But those careful eyes may say, how about this other ambiguity? Pi over 2 or minus pi over 2? At this stage, we cannot say much. We have to wait till we proceed further to identify the angular momentum as the generator of the rotations. At least we'll do it for the orbital part to demonstrate that orbital angular momentum is the generator of rotations in the ordinary 3 space. Of course, spin has nothing to do with any space motion. It's intrinsically quantum mechanical, but as I will demonstrate soon, it satisfies the same commutation relations as the orbital ones. So we can do the same, we can attribute to it the same meaning, saying that they are the generators of the rotations in the spin space. Then comes the important question, whether your system is a right-handed one or a left-handed one. The reference frame that you are using is a right-handed one or left-handed one. Let me plot a picture for this. For example, in the XZ experiment, we could repeat it for the YZ experiment, but in the XZ experiment, if you are deciding on this second option, which one of the signs should be chosen, if this one is given, you are free to choose the following third axis. X, Y, and Z. Well, obviously, this is a right-handed frame. Or you can choose, there is nothing which forbids you from doing that. X and Y, that's a left-handed frame. Spin is the generator of rotations in such a frame or in such a frame, then we'll eliminate the final ambiguity of choosing minus pi over 2 or plus pi over 2. If we choose the right-handed frame, as I said, this is left to a future discussion, which we will complete eventually. If this is the one, this is given, and we decide on the one, this will be chosen, and this will give us the delta 2 plus pi over 2, not the minus pi over 2. The other one, the lower one, would correspond to the minus pi over 2. So we are done. I can write the plus minus x eigenvectors 1 over square root of 2 plus minus. Remember, when you drop the sub indices, default ones are z bases. And the plus minus y 1 over square root of 2 plus e to the I delta 2. Delta 2 is pi over 2. E to the I pi over 2 is I. These are the plus minus y. Once the bases are constructed, finally, up to overall phases. Notice that up to overall phases means there could be, in principle, a phase arbitrary at the very, multiplying the entire thing. But we have determined all the relative phases. That's the best we can achieve. And this was an easy one, even determining all the relative phases. You may say, why it's so difficult? If it's a complex space, an arbitrary superposition of an arbitrary vector would involve two complex numbers. Two complex numbers is 4 real numbers. And you have only what? You have a normalization condition, which gives you one real condition only, normalization of the coefficients. Mod squares add up to 1. 4 minus 1 is 3. And 1 is an overall phase gone. There are 2 more left. 2 more left, meaning one is relative phase, the other is that ambiguity. And that's really why we had difficulty. You have to be very liberal and very honest. You cannot sweep the dust under the rug, right? You have to leave everything in. That's what we have done. We have left everything in, and therefore even this one should survive as an ambiguity, and that could have been only decided afterwards, as we are going to see, through another means, through that interpretation of angular momenta as the generator of the rotations. One final thing before finishing it today is the construction of Sx and Sy explicitly. Remember, at the first stage, we have been able to handle everything about the z component. We have been able to, the basis vectors are given as a default complete set in the spin space, eigenvectors of the SZ that is, and we have been able to construct the SZ matrix representation in that basis being diagonal. It was only natural, 1 and minus 1 sitting at the diagonals. Now we are at a position to determine now Sx and Sy. Okay. So what is Sx operator and Sy operator? Using the standard theorem again. What was the standard theorem? The sum of the projectors add up to 1, and for any operator, the operator can be represented in terms of eigenvalues times the projectors sum over all the spectrum. So what is the Sx operator? Eigenvalues. Well, eigenvalues are always h bar over 2 minus h bar over 2 in any direction. That's Stengerla. Split into 2. That direction is up to you to decide. You call it x, x, y, y, z, z. Any direction, you'll have a parallel and anti-parallel alignment, that's all. So there is no problem about h bar over 2. So what is the projectors now? Plus x. Now let me even be a little pedantic and let me write it as such. H bar over 2 is factored. You have the plus and x's and minus x's. But plus and minus x's we have been able to determine at the end of the day. So you substitute that expression. What do you get? You get the following. Now substitute for the x's, plus x and minus x in terms of the plus and minus z's explicitly given. I assign it as a private homework. Please complete that exercise. It's not that difficult, obviously. You get the following. Plus, minus. I dropped the indices, meaning I went to the z basis now. And I repeat the same for the Sy. Using that theorem, h bar over 2 and minus h bar over 3 are the eigenvalues. This one will be h bar over 2 now. Starting is y, y. I'm really sorry. I correct this. Plus, plus, minus, minus, because that's the projectors, right? Fine. The same here, y. Again, let's be pedantic. Plus, minus h bar over 2, minus y, minus y. Then you take h bar over 2 out and write the y's, plus and minus y's in terms of the z's as such. You get the following. At the end result I'm writing. In the z basis. I invite you to really fill in that gap, which wouldn't take for any of you more than 5 minutes. Write those x's and y's using those expressions, substitute and see those things coming in the z basis. Z is our default basis. As we have started by computing the matrix element of the SZ in the Z basis, of course you are expected to construct all the other matrices in the same basis in order to have any meaning. Whichever base you use for one operator, you have to use the same basis for the other operators. So, what is the matrix representation of these now? What do I do here is Sx. Let me circle this in different color. This is important. This is Sx. And that's Sy. I will now write the matrix representation of this in the Z basis. That's important. That's our default basis, and SZ is represented in that basis, and the plus minus Z's are represented in that basis as 1, 0, 0, 1, remember? Now what are these? I have to sandwich these between plus plus, minus minus, plus minus, minus plus. I have 2 by 2 matrix, right? So you get Sx, the matrix of it is H bar over 2, 0, 1, 1, 0. That is the plus plus, plus minus, minus plus, minus minus representation. And you do the same for this. Sy, H bar over 2, 0 minus I 0. Remember, you had SZ before, H bar over 2, 1, 0, 0, minus 1. Now let me list the matrix representation of the bases. These are the operators. You see, we are constructing the Pauli algebra. Isn't that nice that we could do this from really from the very basic axioms of the quantum theory? We are constructing them. We are not writing them down. We are constructing from the first principles. Remember, plus minus Z were 1, 0, 0, 1. How did we construct this? We had taken plus, projected on plus and minus, we get 1, 0. This is 0, 1. And what about the plus minus x? 1 over 2, 1, 1. 1 over square root of 2, 1 minus 1. You just take these and go to the basis, plus minus Z basis for each of them. And what about the plus minus y? 1 over the square root of 2, 1 over I, 1 over the square root of 1 minus I. Finally, remember we had these strange operators that we defined, which were anti-Hermitian. That's why I call them rather strange. They were introduced. These are anti-Hermitian, and we had the following matrix representation for these before. Then you recognize them now. They were just created like that, and we now realize that S plus minus 1 is nothing but Sx ISy. You just add them up, multiply this with an I, that becomes 1, that becomes minus 1, you add them up, there's a 2 opposition, killing the h bar over 2, giving you this. You subtract, and the lower one survives, 0, 0, 1, 0. Okay, we are reaching towards the end, and not only that, we are illustrating the basic elements and postulates of quantum theory. We are really constructing the spin 1/2 problem very carefully as a byproduct. Now we have all those things in terms of the basis vectors and matrix representations. We can now check the following. Do they commute? Well, these operators, do they commute? Or everything vis-a-vis the sequential Stangerla experiments were an indication that they were not commuting, because once we measure one after the other, all the previous information was lost, meaning that interfering with through a measurement gadget is an order-dependent thing. So, and these Sx and Sy probably, as they are not measured simultaneously, they were order-dependent, that they were not commuting. There's an indication there. Well, now it's for us a free exercise to verify that. You can consider that combination, and through these explicit expressions, easy thing is take those matrix representations that we have found, which is that times that minus the opposite order, which is h bar squared over 4, 0, 1, 1, 0, 0 minus I, 0 minus, sorry for the pedanticity of this exercise, but sometimes pedantic things are rather educative to consider. So what do you get? H bar over square over 4, what is the first matrix? I, 0, 0, minus I. That's the first term. This is minus I, 0, 0, plus I. Take the difference, you get 2 i's, or take the 2i out, write it as I times h bar squared over 4, 1, 0, 0, minus 1. Sorry, there is a 2 out, so h bar squared over 2. You can write it further as I times h bar over 2, 1, 0, 0, minus 1. And you already recognize this as the first, where was it? Somewhere we erased, I guess, SC. En yukarıda, down, yes. Nice, isn't it? We had a beautiful algebra coming out. I can now write it in a more general fashion, which is, I invite you again to check on your own, please, explicitly. You have all the tools exposed to your enjoyment. IJK is in cyclic order, and any two, one x with y, y with z, x with z, satisfy that algebra can be verified immediately with the help of these explicit things. There's another nice thing. Consider the operator defined as sx squared, sy squared, and sc squared. You can either use the operator expressions using the bases here, or use the matrix representation. As we have had this beautiful matrix representation, it's so comfortable. Use not equality, but the correspondence. You write the matrices. What is the square of this matrix? H bar squared over 4 is there. 1, 0, 0, 1. Multiply it with itself. It is 1, 1, right? The unit matrix. Similarly for all, the unit matrix plus the unit matrix plus the unit matrix is equal to 3 over 4 h bar squared unit matrix. So S squared has this matrix representation. A constant times the identity matrix. Strange, isn't it? Being an identity matrix, that thing commutes with anything, right? Any operator, including any component, Sx, Sy, and Sc. How interesting. Well, it's more general than that, really. Well, here, for the spin 1/2 case, that everything has a 2 by 2 matrix representation associated with this, and S squared having a identity matrix corresponding to it. Obviously, identity commutes with any matrix, any operator. Therefore, you may wish to think that it is due to that feature, that it is identity, that therefore S squared commutes with any component, that Si. Not really. You can use this general commutation relation, which will be at the foundation of this generator identification that we are going to do eventually, being the generator of a rotation group, SU2 group, really, 2 by 2 unitary matrices. So you can, it is more general than that, this implies. It is a consequence of this that follows from, in general, from the original algebra. In general, from algebra. Si Sj is IH bar epsilon Sk. Private homework. Demonstrate using that algebra that it is always S squared commutes with any component of Si. Use this algebra to prove this statement. This is trivial. It follows, obviously, without any problem, being identity. But, for example, for higher spins than 1/2, for spin 1, spin 1/2, spin 2, spin whatever, of course, the S squares are not proportional to identity. But still, for all of them, S squared commutes with any component of it. That's why we can eventually, we'll jump into that next week, we can define a simultaneous eigenvalue problem for S squared and any chosen component like SC. We are going to solve the simultaneous eigenvalue problem for S squared and SC together, for instance. So I think that's it.